Hello, in this tutorial I will show you how to use attractors in your Grasshopper scripts. I prepared 3 very simple definitions that I will do from scratch as I will be explaining all the required elements. So the first one is using a linear attractor, and basically I'm using those elements to filter out points from an underlying grid, and then I'm using some calculations to adjust the radius of the circles that are drawn on top of these curves according to the distance from their centers to those curves. Then in the next tutorial I will show you how to use a clipped output of the remap numbers components. It bases on very much liked Voronoi diagram, unfortunately, but I know that this kind of exercise is quite popular, so I will use it as well. And the last one, I will show you how to apply attractors for such a wall. Let's say that these are lamels and they are rotated according to the position of a point in this case, but you can imagine that this point could be replaced with something like position of sun, for instance. For whatever reason you might want to design a building based on a single position of sun. Anyway, attractors in their basic logic are just some elements in the file that are controlling quotation marks, controlling other geometry by distance between this geometry and the attractors. Okay, so let's start. First, let's start from one of the components that will be very useful, if not required, in order to work with attractors. And this component is called cal pattern. So when and how do we use cal pattern component? Basically, we use it whenever we want to filter out some data based on a logic condition. So I will create a square grid of points, 25 by 25 points. Please note that I'm flattening the data here. It's quite important. So right click on points and select flatten data. Let's say that I want to keep only points that are within a certain range from another geometry. And this geometry in my case would be a curve. I will model a curve in Rhino. So here is our curve. Let's say that it represents a river, and those points are possible settlements, and I want to filter out all the points that are too far from the river. How would I do it? So I need to measure the distance between every of these points and the curve. So if you want to measure distance between a point and any other geometry, then, well, you need to find a proper component. In this case, usually the geometry that you want to measure to will determine where this component would be at the top. So if I want to measure to a curve, then I will go to Curve tab, Analysis, and you will find a Curve Closest Point component. A similar component is there for surfaces, surface analysis, and you also can find surface closest point, BREP closest point. This one is for surfaces, this one is for more complex objects, polysurfaces. Anyway, you can find a component which is suited for your kind of geometry. And now I will input points and curve to this component, and on the output and distances I will get a list of distances between between each of the points and the curve. And you need to understand that these two lists are aligned, which means that The distance with index 0 is paired with points with index 0. So they both have the same length, and the items on those two lists are corresponding. So now I need to convert this list of distances into something which is called cal pattern. I will input all of these points just as they are into the cal pattern. I will disable the preview of the points of the source grid, and this is what I receive. You can clearly see that I have less points than there were in the source list, and this is because of this culling pattern, how it is called. By default, the culling pattern is specified as false, false, true, true. What does it mean? Well, let's say that we have a list of elements and another list which is our culling pattern. False, false, true, and true. And every item that has a corresponding false value with it will be discarded. So the first point was discarded, the second point was discarded, but the third and the fourth point, they have a corresponding true value, which means that they are okay. So they pass through. Only those are filtered out. And what happens if cal pattern is shorter than the list that we provided? Well, then it is repeated. So again, we have false, false, true, true, and so on. So this will be discarded, discarded, this goes further. So this is how cal pattern works. And what you have here as an input, you can notice the icon, and the icon represents something that is called a Boolean value. A Boolean value can be either true or false. Boolean algebra is at the root of computation, let's say, of our computers. We operate on zeros and ones. So what you have to input in here is a list of true and false values. I mentioned zeros and ones binary system, and actually it doesn't matter what kind of notation you will use. You can either use false and true, so you can, for instance, in the panel, you can write, of course, use multi-line data. You can write false and true to represent those Boolean values, and then you will get a different culling pattern. Or you can, once again, using multi-line data, you can provide values, ones and zeros, and every zero will be converted into a false value, and every one will be converted into a true value. So whatever you prefer. But as you may already predict, this is not very useful to... Maybe it is useful, but in certain situations, but in our case, it's not very useful if we would have to specify those two lists manually. So we need to find a way to convert those distances into true and false values. So we need to ask a question. And this question, in this case, is the distance smaller than a threshold value? So we need to, first of all, we need to set some threshold distance. I will specify it by a slider, so it will be a variable between 0.1 and 10. And now I have the list of distances and this threshold distance, and as I said, I need to ask a question. And those questions are called logic operators. You have four of, actually comparison operators, sorry, in this case. You have four of those. So you can test for equality, you can test for being larger, one number being larger than the other, you can test for one number being smaller than the other, you can also test for equality, but with a certain tolerance, and there you have also logic operators, which you might know from maths classes, where you can combine different logic conditions. Actually, you can combine zeros and ones, or so you can combine Boolean values. So you can these are simple logic operations like true and false gives you false, true or false gives you true, whatever. We won't get into details with those. For this situation I need smaller than, because I want to test if the first number, distance, is smaller than the second number, threshold distance. And now, instead of list of distances, or this component processes the list of distances into a list of true and false values. So now every point has either true or false value attached to it. And now I can use it as my calling pattern. From what I see, nothing or no point is within that distance, so I will increase it. And now you can see that the filtered list is actually changing as I am changing the distance. So this is how calling works, or how call pattern works, basically. So it requires a list of Boolean values, which is called a call pattern, and you can use some other data in your script, like distance, for instance, to get those Boolean values. So you can test for, as in this case, for a minimum distance, or you can test for equality, whatever. Call pattern is used for filtering data. You have to remember that. Okay, so let's proceed and add an attractor to our to the model. An attractor, as I explained previously, very briefly, is such a geometry that controls the other by proximity or by distance that is separating them. And in our case, actually, we have an attractor already in the file. This is this curve, because it already influences our, it influences the output by filtering the data. So we will use it further we will use that distance further, the measured distances, to create circles around those points. And those circles will be proportionally large. There will be, this is an inverted proportionality between the distance and the size of the circles. So we will start from making the circles. So these are the circles around just the points that are left. I can highlight all the others so that you can see what is the base grid. And how do I control the size of the circles? Well, with a slider, most probably, by changing the radius. And once again, I could input such a list of radii that's, the circles around the curve would be the largest, and the circles far away from the curve would be smallest, but it would be inconvenient. So let's use another value from our file. So for the sake of this, let's say that we are experimenting, so I will use the distance from the curve closest point, which I suppose should give me a circle. So per each point I would get a circle with a radius equal to the distance from the curve. So I would expect something like, like that. So every circle should have a radius equal to the distance from the center to the curve. But it's not the case here. And the reason is that here I am using a filtered list of points, so I have 140 points, but here I'm using an unfiltered list of distances, which means that I have more radii than I have center points of circles. And as you remember from one of the earliest classes or one of the earliest tutorials, when one of the lists is shorter than the other, then the last item will be repeated until the end of the longer list, which means that the last point from the last center point will be repeated as many times as we have surplus in those radii. So this is why I have this many circles around the last point in here. So it doesn't look very good. What we need to do is we need to apply the same filtering pattern to the distances. So I will copy the cal pattern component, and now instead of filtering the points, I will filter the distances. So you can please notice that I have two cal patterns, and in one I have points, and in the other I have just the distances, because you can filter any kind of data. It doesn't have to be geometry. So if I use it like that right now, then it will be correct. So every circle is now touching the attractor curve in one place. So I will just move this curve to see what is happening. So as you can see, the pattern is changing, the filter collection of points is also changing, but it's probably still not what we wanted. So I would like to have, because right now the smaller the distance, the smaller the circle. I would like those circles to be larger when they are near the curve. And this is where we need to use a remap numbers component. And this is very, maybe not very important, but it is very often used. So it's good to understand how it works. It's good to master it. So remap numbers component, how does it work? Basically, it works on two domains. So we have two numerical domains. Let's say that one of them, the source domain, is specified as from 0 to 1. So this is the source. And we have another domain, which is, let's say, from 0 to 2. A target domain. And now, mapping from the source domain to target domain is carried by measuring proportionally where the value is in the source domain and getting the proportional value on the other domain. So let's say that I want to remap value 0.5, sorry, and 0.5 is at 50%, let's say, from the beginning of the source domain. And now what I need to do in order to remap from source to target, I need to find 50% of the target domain, which in our case will be 1, because the total span of this domain, of the target domain, is 2. So 50% of 2 is 1. Let's take another example, just to understand how remap works. So once again, I will start from a simple domain, let's say from 0 to 5. And then another domain would be from -10 to maybe 20. So the span of so this is source, this is target domain, and we can remap as many values as we want. So I will try to remap value 1. I will change the color for that. So 1, 2.5, and 5. Let's remap this value, or maybe I will also show you value 7.5, because you can remap values that are outside the domain as well. And this is kind of important. So let's start by finding out or calculating what is the span of the source domain. So the span of the source domain is 5 minus 0, which gives us 5. And the span of the target domain is 20 minus 10, which gives us 30. Because minus and minus gives us a plus. So we have 30. Span is equal to 5 and span is equal to 30. Span or length of the domain. So 1 would be at 20%, 2.5 would be at 50%, 5 would be at 100%, and 7.5 would be at 150%. And now we need to calculate what how much 20% of 30 would be. So 20% of 30, because we multiply by the length of the domain, is equal to 6. Accordingly, so I would write 6, then for 50% it would be 15, for 100% of course 30, for 150% 45. And now those, let's say, proportional values need to be added to the start of this domain. So minus 10 plus 6 gives us minus 4. Minus 10 plus 15 gives us 5. 100% of course gives us 20, because if it's at the end then it needs to meet the end, and 7.5 will be converted into 45 plus minus 10, which gives us 35. So this is how remapping works. You always need to find proportionally the same value. So first you calculate something which is called a parameter. I represented this as percentage because parameters are normalized. So you find this kind of parameter percentage, and then you need to find the same percentage on the target domain. Yeah, this is how remap works. So in our case, we want to remap distances. Let's get our distances. These are the filtered distances. And we want to map them from a specific domain, source domain. We need to think for a while what would be that domain, to target radius. So targets, in this case, will be the range of our radii. So how small or how large the circles can be. The source is the predicted range of distances that we will use, and the values are those distances in this case. So normally I would use a minimum and maximum value from the list of numbers. One of ways of doing that is, because here we need to provide a domain, so we need to construct domain first, and we need to know what is the smallest distance and what is the largest distance. In this case, I would first sort the list, so those distances would be sorted from the smallest to the largest, and then with list item I would pick the smallest and the largest element. As you remember from one of our previous tutorials, when you use list item with default index 0, then if you zoom in and add an additional output -1, then you will get the first item here under I and the last item under -1. So now if I want to have the largest element, then this would be the -1, and the smallest would be the I. And this is my domain. These are the bounds, let's say, of the list of values. So I have the smallest, from the smallest distance to the largest. This is what I will remap. And now I want to remap the smallest distances to the largest radii. So I will need construct domain once again. Construct domain. And first, let's start by thinking what should be the largest radius. I know that these points, we have a spacing somewhere. Actually, the spacing is defined by the size of the square grid. At the beginning, by default, is equal to 1. So I will, in order for these circles to touch with each other, we would need a radius of equal to half, actually. So my domain start would be half, and domain end something very tiny, but not 0, just to have something in the model. So 0.05, and this would be my target domain. And in this way, I am remapping the distance from the points to the curve, I'm remapping that distance into a range of radii. So the smallest, the nearest point with this distance will receive a radius equal to 0.5, while the one that is the furthest will get 0.05. And that's basically the end of this exercise. In further parts of the tutorial, I will explain the other elements. Also, I will explain what happens when you have more than one attractor and what components to use. And I will show you some shortcuts to all of these components.